Shortly about binaural masking level difference. That means if you have same noise and same pure tone to both ears, then tone detection is poor. But if you have poor tone inverted in one ear, tone detection is good. So if the phase is changed, yeah, for the poor tone. Also, if your poor tone removed from the one ear, tone detection is good because you can hear the tone from the other ear very shortly here. Which masking situation is more difficult? You have signal and masker together, and signal and masker at a certain distance. Perceived separation of sources leads to a special release from masking SRM is okay. So if you separate the sources and masker, it's easier to listen to. The inter-oral time difference is better. ETD leads to perceptual separation of target and interferer. Larger ETDs leads to larger advantages. Altså, larger ITDs means larger advantage. Yeah. Okay, it's easier to listen to. So some curves here. ITD or ILD introduce an advantage. The full head related transfer function FF leads to an even larger advantage. Okay. Yeah. Yes. So okay. It's going better with the FF. Yeah. 8 RTF. Okay. Yeah. And of course, when the azimuth is 90 degrees or you're in front. No, when the noise azimuth is 90 degrees, it's easier to hear difference between right and left ear, of course. Yeah, at 0 degrees azimuth is difficult. Also at 180. In front, the noise is signal masking just in front or just in back of you is difficult to hear separate. Yeah. The tasker and the target and the interferer. Better ear listening. Which situation is more difficult? Two maskers at a spread from a signal with a certain distance, or a signal and a masker at symmetrical about the signal. Auditory system can use the ear with a better SNR. Speech intelligibility is reduced when maskers are symmetric. Then it's reduced. It's better to, it's not symmetric. The listener. We have speech material, talker, channel, listener, response. Okay. What factors about the listener influence the ability to understand speech? Yeah. And of course, hearing loss. I've heard about it. Median hearing loss due to age. And when this hearing loss is growing from 20 years until you are 70 years. I don't know. I'm soon 71 years. I don't know. It's getting worse and worse, maybe. Auditory filters. Upward spread of masking. Normal hearing have the frequencies is not that much spread. Hearing impaired, there more spread of masking. Yeah. So you can see on the curves, normal ears, there's narrower auditory filters than impaired ears. Yeah. What do we want listeners to do? How might we affect the results? So then we come to predicting speech intelligibility. There are some methods or models, articulation index, AI, speech intelligibility index, SII, speech transmission index, STI, and speech envelope power spectrum model, EPSM. Okay. Uh, yes. Speech envelope power spectrum model. Okay. Developed here at DTU, the last one. There are many other not covered in this course. Okay, we start with articulation index, AI. And shortly, how do we calculate audibility? Importance of different frequencies. Acoustic measurements for each band. Okay, speech level S, noise level, hearing threshold, and then we calculate the noise level N. 3 A what's called articulation index E is the speech level minus max of T and N. And if the AI is this index is have to be in between 0 and 30. If it's less than 0, we set it to 0. If it's more than 30, we set it to 30. Shortly, I have to be shortly here. We have this articulation index is a sum of some parts. The articulation index is a number between 0 and 1. So we define n frequency bands, assume a contribution from each band is independent of each other. We have some frequency independent frequency bands, and we have importance of frequency bands is called this sigma. Is called this index E. I index I, and we have audibility of spread in bars E. This is a function of hearing threshold and noise masking. Yeah. So the sum of this, all of these numbers that are in frequency bands, it gives this AI. And then we have to, after we convert it to intelligibility, you have a first axis index, articulation index, and the second axis percent of syllables, words, or sentences understood correctly. If it is very well-known sentences, so you don't need much articulation index to understand much. But if it's nonsense syllables or strange words or something, you need more articulation index to higher articulation index to get a higher percent. Okay. So correction from visual cues, you have calculated AI from 0 to 1, and the first axis, second axis, effective AI with visual cues. If you use yeah, so it's increasing. Yes, you can say calculated. Okay. Yeah. Yes, I'm just wondering a little bit. Yeah. Visual cues, it will be better. For instance, for a 0.5 calculated AI with visual cues, it will be more than 0.6. Okay. So it's a little bit visual cues improve the understanding. Then we have speech intelligibility index. It's based on AI concepts. estimating audibility, A index I, 3 inputs, measured speech level, noise level, threshold, hearing threshold, and standard includes data for EI and TI. We only need to measure noise. So that we have this extra. It's also including shout, loud, raise, and normal sounds. Else it's the same formula as same kind of formula as in AI. SII has the same kind of formula as a sum of the contribution from independent frequency bands. We can't model everything. Scope predictions are correct only on the average, that is across a group of talkers and a group of listeners of both genders. Only on average. Is limited to natural speech, normal hearing, again, stationary masking noise. Okay. Then we come to this predicting speech intelligibility using the modulation domain. How can we account for revelation? A little bit complex. SNR-based features do not work here. Doesn't account for signal interfering with itself. Now we're talking about modulation. Need a new feature or metric. If we repeating function of inner hair cells, its transformation from mechanical to intercellular potentials. Low frequency, you get fine structure. High frequency, it's envelope. Temporal in modulations are the rates of changes in amplitude of the intensity envelope. Yeah. Yes. Temporal modulations belongs to changes in amplitude of the intensity modulation. Simple model, hair cell model. Half wave rectification plus low pass filtering. And FC is about 1 kilohertz. So we have a modulation transfer function. Complicated. Your speaker with transmitted speech signal with modulation index MD equal to 1, and then there's auditory, some listening, received speech signal modulation index less than 1. So you can get this modulation transfer function. It's a function of the modulation frequencies. If we got an M. So this M is a fraction between M2 divided by M1. M2 is the public listening and M1 is the speaker. Modulation can be reduced to by added noise, reverberation, distortion, peak clipping, and so on. Principle reduced modulation means reduced intelligibility. So we get some calculations here, and we get an STI, speech transmission index. Okay. We have a modulation transfer function, and we get some we get some numbers, and we translate it to a speech transmission index. And this is a sum of many things. For instance, if you have some frequency bands, you have some octave bands, for instance 7, and you have 14 octave bands. Then the STI is a calculation of average of some numbers, some contributions, 14, all 14 octave bands, and then the 7, and then we add also the 7 octave bands. So you can say it's 97 times 14 is 98 numbers. And you get a summation of this. Yeah. Okay. So you translated the STI to intelligibility as before. So, and RASTI is a more fast.